Next, we have Dr. Daniel Labuz presenting early functional analysis on the pulmonary hemodynamic effects of transamniotic stem cell therapy, Trascet, in the Nitrofen model of congenital diaphragmatic hernia.
Good morning, and thank you for the opportunity to present our work. We have nothing to disclose. Despite advances in care, CDH remains a highly morbid condition, driven in part by a combination of pulmonary hypertension and cardiac dysfunction. Mesenchymal stem cell therapy has been described, both experimentally and clinically, as a novel treatment option for pulmonary hypertension and heart failure of different causes. On that basis, the concept of transamniotic stem cell therapy, or Trascet, using mesenchymal stem cells as donor cells, has been previously applied to the Nitrofen rat model of CDH, in which it has been shown that the therapeutic effects are centered on the pulmonary vasculature and cardiac remodeling. However, those previous studies only involved structural and transcriptional data, with no functional analyses at all. So, we sought to determine whether the histomolecular effects of Trascet we see in the CDH model actually translate into any impact on pulmonary hemodynamics and cardiac function at term. So, in our experimental design, 13 pregnant rats received Nitrofen on gestational day 9 to induce CDH. From here, we divided each dam into one of 3 groups. One group was not treated, while the other 2 received volume-matched intraamniotic injections on gestational day 17 of either saline or MSCs. Functional analysis was then performed at term with healthy fetuses for control. The MSCs themselves were syngeneic cells obtained from the amniotic fluid of Lewis rats, with their mesenchymal progenitor phenotype confirmed by flow cytometry. To augment their natural anti-inflammatory role, the MSCs were primed by exposing them to interferon gamma and interleukin-1 beta 24 hours prior to administration. Functional analysis was then performed at term using high-frequency ultrasound, with the fetus still in the uterus under placental bypass. While not ideal, this was necessary since the model is not survivable for long after delivery. Also, because of the physiology of the disease under prolonged anesthesia, we were only able to obtain usable data on 8 to 13 fetuses per group. The fetal pulmonary vascular resistance was estimated by examining the Doppler flow in the main pulmonary artery. Specifically, we measured the time to peak velocity, known as the pulmonary artery acceleration time, or PAAT. And we also documented the overall contour of the Doppler flow profile, which is an additional sign of increased pressures with a sharper profile indicating higher flow resistance. Likewise, cardiac function was evaluated by a method called speckled tracking echocardiography, where the lining of the ventricles are tracked in order to determine the displacement of the ventricle wall over time. This was used to calculate global and segmental longitudinal strain using image processing software, and also to estimate the more basic performance metrics such as ejection fraction. Okay, on to results. For the pulmonary artery Doppler data, there was a significant improvement in the PAAT using Trascet compared to the untreated and sham groups. Similarly, the peak sharpness was actually normalized with Trascet. Both of these findings indicate functionally reduced pulmonary vascular resistance following intraamniotic stem cell therapy. To help illustrate the speckle data, here's a representation of how the imaging software determines the strain by calculating the displacement over time vectors for a series of speckles lining the interventricular wall. Results showed that the global longitudinal strain in the left ventricle was impaired after Nitrofen and not rescued after any of the interventions. The strain data in the right ventricle were essentially unchanged across the groups. Both Trascet and sham injections resulted in reduced ejection fractions in both ventricles. Besides the necessary presence of fetal physiology and the relatively short time window for the hemodynamic assessments, there were several additional limitations. The need for general anesthesia and a laparotomy, while being the same for all groups, could have impacted the absolute measurements. Also, the nature of the Nitrofen model and the low number of subjects did not allow for analysis of the distinctions between left and right-sided CDH. Despite this, we can conclude that Trascet improves pulmonary vascular resistance in the Nitrofen model of CDH. At the same time, at least under placental bypass, there is little to no impact on the cardiac function in this model. Still, combined with the previous structural and transcriptional data, these results support the continued examination of a potential clinical role for Trascet in the prenatal treatment of CDH, probably by testing it in a larger animal model next. And I'm grateful to my co-authors, our funding sources, and to all of you for your attention. Thank you, and open to any questions.
Thank you. We'll open this up for questions. While we're waiting for more questions, I have a logistical one. As someone who has very little knowledge of your particular model, it sounds like you were limited by the physiologic response under anesthesia. How did you then, what is your system for actually going through and doing these models? Is it a systematic, we take the pup who's in the left upper quadrant first, or is, like, how does that introduce an error?
Right, so a lot of it improved with time as I got better at doing fetal ultrasounds, because it turns out there was a learning curve with that.
Kudos for that, by the way. That looks very challenging.
Like, I have a lot, Fred, the Fujifilm ultrasound rep, was very helpful, but you do a systematic approach and kind of do every pup. I started in the left horn and kind of just go down more medially, and eventually when you're on, we use isoflurane for our anesthesia, which does have some cardiotoxic effect. So we reduce the isoflurane to as low as possible, and once I get to a point where the fetal heart rate is down to, normal fetal heart rates in rats are 180 to 220, and if we get down less than 150, 140, I just halt it and say there's too much cardiotoxic effect from the isoflurane to continue the assessments.
So would you worry that the ones you assessed later would have decreased cardiac function just because you assessed them?
Just because of the cardiotoxic effects.
And is there any way you kind of tried to correct for that in your model?
I mean, I made efforts to reduce the isoflurane. We could use a different anesthesia as well. The issue there was just with our IACOOK and the way we've been doing the model for a long time, that would have to do a whole other application process and change to ketamine or whatever different methods you'd have, and just is an option for later. That is a good thought.
Very nice. Thank you.
Yeah, thank you.
Do we have any other questions for Dr. Labuz? Great. Thank you.
Thanks.